So most designers are aware of the possibilities of additive manufacturing, either in metal, in plastic, in concrete, and with different kind of setups like a desktop setup, a robotic arm, or a big gantry system. But not all designers are aware of the different kind of design principles. So designing for a desktop printer is something totally else than designing for a robotic 3D printing system. And we are going to discuss these design principles in different chapters. We will start with what is robotic 3D printing, like what is the difference between a gantry system and a robotic arm, and how does this translate to your design. Then we will get into the basic design principles. So think about the nozzle size, the layer heights, overhangs, support, and basic failures. We will do this by showing some videos, and I built a comprehensive Blender model in which you can tweak certain settings and see what happens to your print. And I will also use it to explain these design principles. We will get more into advanced slicing. So what if you go beyond just planar into non-planar or variable layer heights, which are related. So a little bit more the advanced slicing directions and custom G-codes. And in the last chapter, I will give some general tips. So think about modular designs if you want to scale bigger, time and cost balance, and material choice. Let's get into the first chapter. I'm going to open the Blender model, and then step by step, I will guide you throughout the process. To explain the design principles, I'm using Blender. Of course, you can design your object for robotic 3D printing in any other 3D design software that you are familiar with. The design rules will be the same, so don't feel forced to use Blender. If you use Blender and you want to receive this file, you can contact me. So what you see is that I plot down all the design rules that I want to discuss today. I made a little interactive 3D model that we are going to discuss one by one. But the main element of this file is a robotic arm that we can manipulate. So that makes it easier for me to explain. I can even let it run some code. So it's just to give it a more interactive element. But don't focus on that too much right now. What makes robotic 3D printing different? Robotic 3D printing is not just a bigger version of a desktop printer. Once you print on a meter scale or bigger, everything behaves different. Small mistakes become big mistakes, like the bead is thicker, the heat stays longer, and gravity starts to play a bigger role. So what works on a small printer with a small design often doesn't work on a bigger scale. So it's not just about scaling it up. So as a designer, you are not only designing the shape, you're also designing how it's made. You are designing the path the robot takes, the direction of the layers, the speed, the temperature, and it all affects the result. Also, every robot has its limits. It can only move within a certain range and at certain angles. And if your geometry falls outside of that range or outside of those angles, it can simply not be printed. So compared to a gantry system, which just moves in straight lines, a robotic arm has 6 or even more axes. That means that it can tilt, it can rotate, and it can follow curves. And that opens up a lot of creative freedom, but it also adds a lot of extra complexity. The surface is another big difference. With robotic 3D printing, the layer lines is not something you can hide. They are thicker, they are bigger, and most of the time you want to make them part of your design. So the way the paths are drawn can give extra texture, reflection, and character. Then there's heat and time. The material stays warmer for way longer, so that can become an issue. For example, if you are printing really thin lines or straight walls, the objects tend to twist or bend. So curved or thicker layer lines tend to work better. Then there is that every setup is different. Different robots, different nozzles, different materials, and it all affects your design. So it's important that you work together with whoever is running the machine in an early stage. Because in the end, it's all connected. The material, the design, the process, And once you start to connect those things, you can design specifically for the process instead. And that's where you can get the nice results. So what are actually the design rules that you have to think about? Well, that's what this whole video is going to be about. We will first start with some basic design principles. So let's start with nozzle size and layer height. So how does this influence your design? If we look at your outer shell, so if we design, for example, a step file, so a surface-based model. That surface-based model is translated to the printer through different settings. So the settings that you can adjust are, for example, the nozzle size. The nozzle is the output of the print head. So granular goes in and a printing line comes out. Those printing lines can have different kind of settings, but there are some basic settings. So for example, a system that I use, most of the time we print with a 6mm nozzle and we have a layer height of between 2 and 4 millimeters. That looks like this. But for example, if you go towards 10 millimeters layer nozzle width and a 4mm layer height, you get something like this. So you will directly see the difference in your model. So if I hide, for example, the model, you can see how different kind of settings will adjust your appearance. So it is important to understand that you can tweak these settings. You can go with a basic nozzle size that the manufacturer already allows, like 4, 6, or 8 millimeters, and you design with that in your mind. And you can think of a certain layer height that you think works with your design. You have to understand that those nozzles are quite standard. So it's a mechanical nozzle, so varying it is something that is possible, for example, by using some overflow within the printing. But that's something you have to discuss with the manufacturer. The layer height is something that you can tweak as well, but you have to consider some things that we will discuss in the other parameters. If you think about your nozzle size correctly, you want to make sure that your objects are using a multiply of the wall thickness. If you are going to design an object of 16 millimeters, you can use a nozzle of 8 millimeters and do 2 contours. For example, what you see here on the left. If you are going to design an object of 20 millimeters, for example, this object, then you have to be aware that you cannot use 2 contours of 8 millimeters because then there will be a little gap in between, and that's something you don't want. So then you have to consider using one nozzle of 10 millimeters. Or you have to, if they don't have the option of 10 millimeters, you have to consider reducing your walls to 16 millimeters. What you can also do is you use a smaller nozzle and you create 3 contours. So the main message is you are designing with the nozzle width. The nozzle width cannot be changed during the print. So within your whole object, you have to consider the same nozzle width and design with that nozzle width. Okay, then the next thing that I want to discuss is these are just outer contours and they are not meeting each other anywhere or overlapping anywhere. If you want to create an object that, for example, looks like this. This is your surface model. So if you are creating your surface model, you can decide how these 2 surfaces are going to meet each other. But what you have to be aware of, like if you want to have it like this, for example, and we turn on the layers, the adjustment I just made will result in layers that look like this. So they will not touch, which is fine. But if you want to introduce some extra strength, you can make sure that these surfaces will barely touch each other. That will look like this. This is a little bit too much. So now it's overlapping, and if contours start to overlap, it will create defects because you have extra material. You need to design with the layer width in mind. So if the layers are going to be exactly in the middle of your surface, the space between those two surfaces has to be exactly one layer width. Then they will perfectly meet each other and barely touch, and this will create extra strength for certain objects. For example, in the lounger chair that we have at More Than Layers, you can see that it barely touches, and this creates extra strength within the object. What you also have to understand is that if you want to have some details in your surface, so for example a logo, an embossed logo, or letters, you need to understand that the nozzle width and the layer height are affecting the resolution that you can use for those images and text. So for example, right now there's not any detail in this object, but we can simulate some detail. So if we have, for example, this little blob, and we translate that to layer heights, we see, well, there will be some issues here because of overhang. We can solve the overhang, for example, reducing this. And then if we refresh, we have some detail. This is fine. It's big enough for the nozzle and the layer to cover it. But if we, for example, subdivide this surface a couple of times, and we have a smaller detail level, and we select a couple of them, we extrude these, you see that it doesn't work anymore. If you want to create details, they can never be smaller than 2 times your nozzle. So if we go from details to thin walls, there are some considerations that you have to have in your design if you want to use thin walls. And a thin wall is, for example, 1 nozzle width over a long length. So if you, for example, imagine that this object is 1 meter and you want to create a really thin wall of 1 nozzle width for 1 meter, the plastic is gonna wobble. So it's gonna deform and it's not gonna keep its form. It's not gonna stay strong. So how you can solve this is by adding some more detail, by adding some extra surface. So now it creates extra strength, and you can also make this surface meet the other surface. So you create more strength, and it's not just one long layer, while still on this side you create the effect that you want. So you can solve this by different ways, for example, adding some ribs in between or having some extra curvature within your object. So also in this case, ask your manufacturer, like, what are the right settings for long thin walls if you really need it. If you are, for example, designing a table, you want to have one flat long part, but that doesn't mean that on the other side of your part you can include some ribs or some curvature. This makes it way more stable and less prone to deformation. Which brings me to 6. It's called round corners. Well, what do you think that is? If you have an object like this, you have to imagine that the robotic arm is going to travel over these contours, and if it arrives here, it has to make a direct motion towards the other side. That's not something a robotic arm can cope with. So what it normally does, it starts to slow down as soon as it's going towards the corner, and then it goes that way. It starts to increase the speed again, it slows down again, and that means that you have more material deposition. Also in corners, they tend to curl. So corners have some extra material, they start to curl, and then layer by layer it starts to fail. So a best practice is to give a bevel to these corners. So most of the time you have to think of a radius around 4 times your nozzle width, and then the object will look like this. And that means that the robotic arm can just keep traveling very smoothly on all the corners, and that gives a way better quality for your object. So try to be aware of that. So the next thing I want to discuss is overhang. So an overhang is the angle that a print can have compared to the printing bed. So this is, for example, an angle of, I would say, like 10 degrees. So this is a steeper overhang of like 45 degrees. If we refresh this one, you can see what happens to the print. So what do you have to think of with overhangs in robotic 3D printing? So most of the time, an overhang of 45 degrees is allowed, and after that it gets more critical. So I do know some manufacturers who can go up to 65 degrees, but you are really going towards the boundaries. So what you also have to think of, if you use really thick layers, the maximum overhang reduces because there is no material for the next layer to deposit upon. It also works the other way around. If you have really thin layers, you can have a way steeper overhang because there is material that the next layer deposits on. So if you need to have a really big overhang, most of the time you will reduce the layer height. We will explain later why a really low layer height is not always recommendable. That brings me to bridging. So what is bridging? Bridging, if you imagine this part being printed, these layers are going totally fine, although you have to bevel the corners. But then as soon as it arrives here, it has to print an island here, then it has to travel to the other side, and then it has to start printing here, go back to this side, print here, or it does first this one and then this one. That means that your robotic arm has to travel from one side to the other side. And what happens with your material flow? Well, on most setups, the material flow will just keep going. So that means that it will deposit in between here. It will still deposit material. That's not what you want. Some manufacturers have what's called a melt pump, and they can adjust the material flow so they can travel from one side to the other. It's just not a very common thing at the moment. So the best thing to do is to create designs in which you don't need to travel from one side to another. So bridging, better to not do it. So what about heat control? So what do I mean with heat control? So every layer cools down and has some residual temperature as soon as the next layer arrives. This is something good because that means if it's still a little bit melted, it can stick to the next layer. It's also something bad because if it's too hot, it can collapse. If the layer below is too sticky, it doesn't print correctly. So a common thing that we do in the design is that every layer is around 1 minute printing. So then it has enough time to cool down and is still warm enough for the next layer. But if you look, for example, on designing a cone, you see that the top layer has only a really short print path. So it doesn't have time to cool down, or the printer has to go really slowly. But if this is just 10 centimeters and the bottom part is like 3 meters, that means that the higher you go, the more heat it will keep because it's gonna print faster. So instead of ending with a point, so it's a good practice to end, for example, instead of at the point like this. So the top layer has a little bit more length, so it has time to cool down. So don't end in points. So let's talk about building volume. So what is actually the building volume of a robotic setup? Let's think about it. Normally we have a building volume of a cube. So if you look at the gantry system, you have a X, Y, Z maximum, and within that cube you can design your object. But with the robotic arm, it's a little bit different. If we imagine a stationary robot, so without a rail, so we have the movement into Y, we have a movement into X, and we have the movement into Z. But you can imagine that if we have a movement into Z and then we do a movement into Y, it cannot go as far as that it can do over here. So if you look at the movement of the robotic arm, we have a Y, we have a Z, and we have an X. But the further you go into the Z direction, the less it can go into the Y direction. So if we are on top of here, it can do like this. Same for the bottom. And that's the same for the X direction. So the further you go towards X, the less it can go towards the Y. So that means that if we create the robotic motion, so you end up like something like this. You can go here, you can go here, you can go to that side, you can go up and down. So your print volume is directly affected by the movement that your robotic arm can make. Something within this cube is possible, but as soon as you go higher, you see that it goes out of the boundaries of the robotic arm. So if you want to print higher, most of the time, that means X and Y have to be smaller. So this is different for every setup, because some setups, for example, can move over the X direction. And that means that, for example, you can scale way further over the X direction. So service bureaus or manufacturing services, they all have their different kind of system, which have different settings and that translate to different design rules. So best practice is that if you are thinking about designing something for a robotic system, already include them early into the process. So what are the best practices, like which materials print well on their setup, what nozzle do they prefer, what layer height can they cope with, and also some advanced slicing settings that we will discuss after this. So what I recommend is to go to adidex.com, and this is a map of all the robotic 3D printing companies in the world, and you can select company type, manufacturing services, and then you can check in your region, like for example La Máquina, Nagami, 3D Maker Zone, HB3D. Those are all manufacturing services with robotic arms. So here you can go with your design and they can make it reality. But they all have their different kind of setup, and it's good to involve them in an early stage of your design process to be sure that the design that you are working on can be printed on their setup. So now that we cover most of the basic principles and design rules for robotic 3D printing, it is time to go more towards the advanced settings and advanced slicing strategies. And I can imagine that by now you are thinking like, okay, can it not be simpler? In robotic 3D printing, there is something that is comparable to a slicer in desktop printing. We call them advanced toolpath planning software, and two big players are Additive and AI Build. So what they made is software where you can plan your robotic toolpath, and you can print beyond planar. So that means that you don't have to always do layer by layer in only one direction, but you can have multiple layers into multiple directions, or you don't have a printing layer at all. So that's what we want to discuss right now. Also, like in the previous part, I already mentioned that you have to consider which kind of setup your manufacturer is using. Also, you have to consider which kind of slicing software they are using. Are they using Additive? Are they using AI Build? And what are the boundaries of those software packages or the opportunities? That means that you can get ahead of your competition if you use these advanced slicing options, because now the market has been mainly planar. So what do I mean with that? If we, for example, go back to our examples in Blender, if we slice something purely planar, and this is our object, and we slice it purely planar, we see that we get these kind of printing layers. And that's not how you want to end. Like, these kind of steps are not pretty. So how you rather want to have it is in the next example, and this is what we call multi-planar. So you start on one plane, printing plane, and slowly it transitions to an end plane, which is in an angle. Planar means that the print nozzle will go into only this direction. So it's only in the X and Y active, while if you turn this axis, you see that the robotic arm can also print under an angle. So instead of going straight, it can print under an angle. That's called multiplanar. So what you can do is you can manipulate, for example, this angle, and it will start to calculate which layers it will need for that. And that means that on the left side, you will have a higher layer height than on the right side. That means that your machine needs to be able to do varying layer heights. Not all setups can do that. And there's a boundary to it. So it's not unlimited. On the right side, for example, you need to have like a minimum layer height, let's say 1 millimeter, and that translates to a maximum layer height on the other side. So that's tweakable. Then if we go one step further, we have non-planar. What does non-planar mean? Non-planar means, like in the previous example, we had planes that go towards another angle. With non-planar, there is no printing plane at all. If you have, for example, this object and you want to print that in a nice way, this is not going to be the way, because then you again have those steps that are going to be ugly. It's going to look like stairs. So the way to do that is to apply non-planar printing layers. So that's what you see here. In the beginning, the layers are straight, and slowly you see that they transition towards the form on the top. You can do that gradually, or you can tweak it. So now it will have a little bit of a different form. Also with that one, you can play around how you want your layers to look like. It will take some of the lines of the base model and then translate that to the curves. You have some control in it, how that translates. So this is non-planar. There are no planes. It just follows the contour of the object. Then another one is an angled print bed. So if you imagine that this white part is your printing bed, so the robot prints under an angle, so it will move into this direction and in this direction. So that's your first printing layer. And then it continues into this direction. And what happens is that you can print under an angle. And if you have a rail, you can print for a very long trajectory. And this is, for example, used in the boating industry to produce boats. That's angled printing. Then you can also consider using a non-planar print bed. So if you imagine that this is your print bed, and this is your object. You want the object to start with a printing layer like this on top of the curved printing bed, and then produce these kind of starting layers and slowly transition towards however you designed your object. So this is printing on a non-planar print bed. So these are the more advanced slicing strategies, and it's good to be aware of them. There are some more. You can check, for example, AI Build or Adaxis, their documentation, and they explain like the different ways of how you can slice an object. Also what you can use as input and what will be the output. Now you have your object and you see everywhere the enormous layers, and that's maybe something that you don't want. But you can do printing and milling. If the right object is what you desire, you can print with some extra material. So let's say you print it 2-3 millimeters thicker, and then with a milling head on the same setup, you can mill the object. So then you get a smoother object, and it's part of the advanced toolpath planning. You can also program your own G-code. This is one of the examples of the Bubble Beats chair. So the robotic arm is using G-code. This is defining how the robotic arm should move. So if you are able to sketch a line, if you are able to calculate the deposition rate of the material on all the points where the robotic arm is going to, you can create custom toolpaths. And what is custom about it? Well, for example, here you see these kind of structures. So the robotic arm moves one layer like this and the other layer the opposite. And then you get a really cool pattern. So you can play with those. And one thing that I forgot to mention is that warping is a big issue. So your object can start to warp just like desktop printing. But if you go towards robotic printing, everything gets bigger. So your mistakes also get bigger. The warping also gets more severe. These rings are, for example, to mechanically fix the first printing layer to the printing bed. Also, it will be flatter than the top part. So take that into account too. So you can do some surface treatment afterwards. That's of course extra costs. If we are talking about cost, so an important factor for the cost is printing time. So as we saw in the heat control section, we always take more or less 1 minute per printing layer. This is different per setup, but most of the time you are tuning your printing layer to print for a certain amount of time. So if we talk about printing time and cost, they're related to each other. So the material, it's depends on if you're using recycled material or virgin material, but most of the time it's like 20 to 30% of the price as well. And then the labor, so the programming, taking the thing off the printing plate, putting the material in the system. So there are certain things that you can tweak. And one of them is the printing time. If you look at this left object and the right object in volume, they are the same. But because this object you print in this orientation, it takes you around 3 hours to print. The same object sideways is going to take 8 hours to print. If you are going to design a launcher, like a big launcher, print it sideways and not like in the length. Because in that way, the printing time will be reduced immensely and the price as well. So think of objects that are big, that have a big surface area, but that can be printed low. That's where the good business case is. So for example, this object, imagine it as a mirror frame. So if we scale it over the X and the Z. So basically from the side you can see that the objects are as high, so the printing time will not differ that much, although one object is way bigger than the other object. If, for example, this object would be a little bit higher, so the printing time would be twice as much, which means that the price will go up considerably. Labor is another thing that you have to consider. It takes time to take your print off, and it also takes time to do a surface treatment or like adjust certain things. The most efficient is if your object directly comes off the print bed ready. That's never the case, so make sure that it doesn't need a lot of steps afterwards to finish off the project. If your boundary box of the printer is too small for the object that you want to create, you can split it up in different sections. That adds time to the assembling, of course, but it makes it easier to print. So you can print different parts in different orientations, but make sure that you think of a way to assemble the parts in a nice way. You don't want to see thick bending layers between those objects, and you want to mechanically fix it, or you want to glue them together. There are some best practices in the market, so search for those as well. So now that you know all the design rules, it's of course time to start designing something yourself. And if you need some inspiration also for which materials to use, you can use the lookbook of More Than Layers. So in the lookbook, we discuss some projects that we did, some objects, and some materials. So if we look at materials, this is for example a table we made of recycled fishing nets. It's recycled PP. You can see the material in the left corner. Glass fiber filled PP. It's a nice material. They add the glass fiber so it warps less, and it's made from recycled fishing nets. So for these kind of objects, it's really interesting. This looked like custom-made cheat code, but actually it's a surface model. So in this object, you can, for example, see that it was designed with parts that are barely touching each other, which gives it way more strength, because if it would be loose, it would wobble. So that's a good example of how you can use those two layers to touch each other. This was made of fully recycled post-consumer PP as well. So this is another example of a bioplastic filled with wood fibers. So it has more like wood kind of texture. Also the smell, if you print it, it's more like wood. And this one is made of PET, the material that's used to produce water bottles. It has a more shiny look. It does tend to get more brittle. So if you use something that needs to hold more strength, or that you use, for example, a chair that you want to sit on, be aware that it can over time get too brittle and it can break. Then this is an example of how you can combine two separate kind of materials. So if you combine objects with different materials, you can get a different look. So the outside is reused PP, the inside is the material with more wood fiber, and you can play with those aesthetics. Then this is the example that we already saw in the custom-made G-code. And now you see it in reality. So actually you can see the robotic movement very clearly in the object, and you can use those custom G-codes to create really cool structures. And this is another example of that, like a less heavy pattern, same principle. More examples. Then another material you can use is PETG, so post-industrial. I see there's a typo. Post-industrial recycled PETG, which is perfect for lamps. So you can make a more translucent or transparent print. Transparent is hard because you always have some air bubbles or inconsistencies in your layers, and your printing settings have to be perfect. So aim for translucent, I would say. And then this is a nice example of PHA, which is a biomaterial derived from bacteria growth in waste treatment. And you can print this on a big scale as well. And beside the objects, you also can find a list of all the different kind of materials that you can use within large format additive manufacturing. I'm not going to explain them all. Just find the lookbook in the resources and you can take a look at all the different kind of possibilities.